want to give you a quick review over what we talked about today for your test on Thursday. So just in case you weren't able to attend the Google Meets today and you had some questions, so I just want to go over with you some of the things that you need to know for your test. And so one of the things that you're going to want to make sure that you can do, and this is all listed on the news feed for Monday, is that you want to make sure that you can distinguish between acids and bases and salts. Make sure that you know definitions for those. Make sure that you can identify those, and make sure that you know properties. For example, a property of an acid would be that it tastes sour. Property of a base, it tastes bitter. An example of an acid, if you're talking about common acids that you might find in your house, you'd head to the kitchen and you would find something like vinegar, pickle juice, citrus fruits are examples of acids. And of course, from Alien Juice Bar, you learn things like tea and coffee are also slightly acidic, along with carbonated drinks. If you were looking for bases in your house, then there are two places you'd really want to head. One of those places might be wherever you have cleansers located. So like if you have soap in the kitchen or any of those cleansers that you might use in the bathroom, if you have soap, you have shampoo, those are all going to be bases. The other place you'd head to in the bathroom to find a base would be looking for something called an antacid. And of course you did a reading on that for an article, for a video, that was not an article, but a video that you watched about antacids, and they help neutralize stomach acid. And so bases are going to be found as cleansers. They're going to be found in medication. Acids happen to be a taste that we enjoy for food, so we find them with a lot of sour foods. Some other properties, we know that acids react with metals to produce hydrogen gas. We also know that acids and bases together react to neutralize each other. We know that both of these, when added to water, produce ions. And the production of ions makes them listed as an electrolyte. Electrolytes are charged particles that in solution help conduct electricity. So those are just a few properties. You'd want to make sure that you check your notes and make sure that you're very familiar with those. The other thing you want to be able to do is identify an acid and base according to Arrhenius. And Arrhenius's definition, you might notice, typically just centers around a formula. So we know that acids, according to Arrhenius, contain hydrogen, and we know that bases contain hydroxide. And so an acid, an example, might be something like hydrochloric acid. When it dissociates, it produces hydrogen ions. A base might be something like sodium hydroxide, and when it dissociates, it's going to produce hydroxide ions. That's pretty straightforward in terms of Arrhenius. One of the things that you should be able to also do is to name acids, bases, and salts. So of those, we spent some time looking at, and we already know how to name bases and salts. Those are pretty straightforward. So let's look at those real quick. An example of a base might be something like KOH. There's the hydroxide that makes it a base. And so this is back to naming and bonding, and it's just starting on the left-hand side, naming the metal. This would be potassium. And then looking at what's left, that happens to be a polyatomic ion. And of course, because it's a base, it's hydroxide. So this would be very simply potassium hydroxide. When we're talking about a salt, salts, of course, neither of which contain hydrogen or hydroxide. It's specifically something like a metal combined with nonmetals. And it might even be a group like a polyatomic. And so this is just going back to simply looking at what's first on the left-hand side, naming the metal. Copper, of course, is a transition. So we're going to reverse that 2. This would be copper 2, and then what's left? Nitrate, polyatomic ion. So that's really just, we already knew how to name those regardless of the fact of whether they're bases or salts. The acids are a little tricky. Now we reviewed this back in nomenclature, but it always kind of gives us a little trouble when we're talking about naming acids. So for acids, there are 2 general kinds. There are acids that are then combined with one other element, like hydrochloric acid. And in this particular acid, hydrogen with one other element means that it's made of 2 things, and we call that a binary acid. 2 substances. And so for a binary, the template or the form that we use is hydro. That prefix indicates that it's binary. It's hydrogen and one other non-metal. Then you name the anion. In this case, it would be chlorine. But we're going to change the ending to ic, and we add the word acid. So this would be hydrochloric acid. So I always think about that one because that's the one that everybody almost knows the name to. HCl, hydrochloric acid. So if we were to take hydrogen and say combine it with nitrogen. Okay, this once again is a binary acid because it's hydrogen with a nonmetal. So we're going to use the same template. This would be hydro. Now we're going to take nitrogen and we're going to change the ending to an ic ending, and we're going to add the word acid. So that would be hydronitric acid. Now, how does that look different if we have something that's not a binary? So this is the way we name binaries. Well, if it's not a binary, then we have to have a group. Here's an example of a group. So the way we approach this is we look at the group, which in this case is a polyatomic ion. And polyatomic ions have 2 different kinds of endings. The name of this group is nitrate. And so we take that ending and we change it and we make it nitric with an ic ending and the word acid. So 8 become ic acids. Now I can change this up just a little bit. Instead of NO3, there's also an NO2. That polyatomic ion happens to be nitrite, and so it becomes nitrous acid. And so endings on polyatomics indicate what the ending is going to be for the name of the acid. Notice that neither of these have the prefix hydro. Hydro is specifically used for binaries, and if you have 3 or more elements that make up the acid, then you drop the hydro and you're just basing it upon the polyatomic ion. Okay, so naming acids a little more. You want to make sure that you know how to do those. The other thing that we looked at is we looked at Bronsted-Lowry. Now, Bronsted-Lowry acids and bases, what you really need is an equation for that. And so there were several that we looked at. We had this handout, and you want to make sure that you go back and review it. And I just want to pick out 1 or 2 of those to go through with you. Excuse me, and to take a look at. Okay, and so here's a good one that we looked at today. And remember, these equations are going to look very different because in these equations, it's all about the ions. And so before, when we looked at balanced equations, we never had ions. They were always balanced compounds, and that may not be true in terms of what we see for acids and bases. And so here's an equation that we can look at. And one of the things that you should be able to do is, first of all, identify what's an acid and what's a base. Okay? And so according to Bronsted-Lowry, acids are proton donators and bases are proton acceptors. Now, what do we mean by that? Well, when we say proton, the proton is really a hydrogen ion. Okay, and so what we're going to do is we're going to follow the hydrogen. So think of the left-hand side as kind of the beginning. This is the before. We're going left to right. These substances would be what happens afterwards. So starting on the left-hand side, I've got CO3, which is the carbonate ion. Over on the right-hand side, here it is, but what's different is we've added a hydrogen. So notice that it has gained or accepted a proton. And so over here, since CO3 accepts a proton, that makes this a base. Now, water, in this case, if you notice, we're expecting it to be the acid, which would mean that it donates. So let's see if that's what happens. Here's water. On the right-hand side, we have just OH. What happened? Well, if you notice, it gave up a hydrogen. So it donated. So there's our acid. Now, you may say to yourself, wait a minute, water can be an acid? I thought it was neutral. Neither an acid or a base. Well, pure water is, but Bronsted-Lowry is talking about a proton being exchanged in the chemical reaction. And so he defines an acid or base based upon what it does with the proton. And so water is something that we refer to as being amphoteric. And that means that it can be both, or it can be either an acid or base. It depends on what it's added to. So in this case, it was added to a base, and so it's acting as an acid. Check this one out. We have HCN plus water, and we take a look at what we have on the other side. We get the cyanide ion, and we have what's called the hydronium ion. So we're looking at before and after. Whoops, somebody lost a hydrogen or donated it. So this would be our acid. Now I want to point out right here that when you first saw that hydrogen, and you may have been thinking to yourself, wow, that's got to be the acid according to Arrhenius. Notice it's also the acid according to Bronsted-Lowry. So things that we would normally identify according to Arrhenius as an acid are still going to be an acid. Okay, they don't contradict each other. The two definitions work together. Okay, so here's our acid. That must mean that water acts as a base, so it must accept. And if we notice left to right-hand side, sure enough, on the right-hand side, water has accepted a proton, so acid base. Now, the other thing that you should be able to do, besides picking out what's the acid, what's the base, is you also need to be able to identify the conjugate base and the conjugate acid. Really important for you to understand the left-hand side of the equation is always identifying the acid and base. The right-hand side of the equation, the product side of the forward reaction, you're identifying conjugate acid or conjugate base. So let's go back and look. Here the base accepted the proton. And now that it's got a proton, notice that it has the ability now to give up that hydrogen. And if you notice in the reverse reaction going from right to left, that's exactly what it does. So it's going to act now as a conjugate acid. The acid donated. Now, notice going back in the other direction, that hydroxide has a place available so it can now accept a proton, which makes it a conjugate base. Down below, HCN donated and got rid of the hydrogen. Now it has a spot available, so working back, it could then accept. Water accepted, now it's got a proton that it could then donate in reverse. So one of the things that you should recognize is that whatever is an acid on the left-hand side, on the right-hand side becomes the conjugate base. Because once it donates, now it has a spot that in reverse, it could now accept. And whatever is a base on the left-hand side becomes the conjugate acid, because once it accepts, now it has a proton that it can turn around and donate. Okay, Bronsted Lowry, and those are on the news feed. You could go back and check those. Keep in mind that pH scale is that numerical scale that we use to identify. And if we're talking about acids and we're talking about bases, acids have low pH, bases have higher pHs. pH of 7 indicates something is neutral. And we say that the pH scale is logarithmic. That means if we have something with a pH of 2, what that really means is that the concentration of hydrogen is equivalent to 1 times 10 to the negative 2. So that 2 is actually the negative exponent of the concentration. It just makes it more convenient to talk about numbers 1 through 14 than it is to talk about 1 times 10 to the negative 2. Now you notice that these numbers in some cases can be really small. Think about a pH of 13. The hydrogen ion concentration would be extremely small, 1 times 10 to the negative 13. That means that you've got, whoa, okay, too many zeros for me to write down. And you might say to yourself, Ms. Watts, can we even measure that? Turns out we can. Okay, and so keep in mind we're talking about ions in a solution. Numbers can be really small. So acids, bases, and one of the ways that we indicate if something is an acid or base is by the use of indicators, which typically turn color because the shape of the molecule changes when it's in the presence of an acid or base. So its color can change as well. The key one that you should be familiar with from Alien Juice Bar, red cabbage juice. And of course, as an acid, red cabbage is pink. And in a base, red cabbage happens to be green, kind of a green-blue, has a little bit of a blue tint to it. And then, of course, when it's neutral, it's a nice purple color. All right. So those are some things that we kind of looked at for pH. And then the last thing I want to talk about is just neutralization itself. And that was that last handout that we took some time to go over. And so the template for acids and bases is we say that acids and bases neutralize each other. And what they end up making is salt and water. Now we know water has a pH of 7. And you might think, oh, acids and bases, add them together, you get salt water. Safe to drink, right? That doesn't necessarily mean, and just because this is called neutralization, that you're always going to end up with a pH of 7. It really kind of depends. It depends on the strength of the acid and base. If you go back and look at your notes from last week, one of the things that you were given earlier were the actual 6 strong acids. There are a couple of those like HCl, HNO3, and a couple of others listed as well. And so strength is something important. And what that means is that for every hydrochloric acid molecule, each one pretty much dissociates. Something that's not one of those 6, say something like vinegar, think about it. Wow, I would never drink hydrochloric acid, but we certainly do drink vinegar. Well, vinegar is a weak. Strong means that it totally dissociates. And vinegar happens to be a weak acid. And what does that mean? If I look at a container with vinegar molecules in it, most of them are not going to do this, where it dissociates. Instead, the majority of the reaction is going to be found with the molecule still intact. Very few dissociate, which is why it's not harmful for you to drink vinegar. But you'd never think about drinking a strong acid like hydrochloric. Okay, and so on the pH scale, we'd expect hydrochloric to have a very low pH, maybe something around 2 to 3, whereas a weak acid, we'd expect it to be somewhere around 5 or 6 for a pH, maybe even a little above 6. So when you add acids and bases together, you may not get a pH of 7. How do you know? Well, if you were to take hydrochloric acid and add to that a strong base like sodium hydroxide, and bases that are strong are going to have metals from group 1 or group 2 on the periodic table. So strong acid, strong base typically means that your salt and water are going to end up with a neutral salt. And so you'd probably be pretty close to having a pH of 7. If you take something like hydrochloric, which is a strong acid, and you were to add something, say something that's not a strong base, like maybe copper hydroxide, which is a weak base, and you combine those together, you're still going to get a salt. But the problem is that this salt is not going to be neutral. Instead, if you notice, whatever the stronger component is, it's going to overpower, and that probably means that you're going to have a lot more hydrogen left over. That when the hydrogen from the acid and the hydroxide from the base get together and they actually form water, you're probably going to have some of that hydrogen left over. And so what you're going to end up getting, because the hydrochloric acid is stronger, is what we call an acidic salt. And so this acidic salt, which in this case ends up being copper chloride, is not going to have a pH of 7. In fact, we'd expect it to be lower than 7 because of the fact that it's going to be more acidic with more hydrogen left over. And likewise, if we were to come up a reaction where you have a strong base, say something like sodium hydroxide, and you combine with that a weak acid, maybe something like vinegar, and you combine those together, you're still going to get your salt, sodium acetate, and you're still going to get water. But in this case, this is not going to be a neutral salt because they're not balanced. In fact, we would call this a basic salt. Okay, so really quickly, those are some of the things that we talked about over the course for your quiz on Thursday. Be ready for some multiple choice questions over any of this information, plus some of the things that we've been working on from your notes. So make sure you get your notes organized, have those together and ready. You've reviewed them. You should be able to answer those multiple choice questions. If you get stuck on one or two, you got enough time to check your notes, but you're not going to have time to look up every single answer. Okay, so make sure you have everything ready to go, and we'll see how it goes. Make sure you email me if you have any questions. See ya.